Okay, so in this lecture, we're going to discuss about polynomial rings. So we're going to discuss about polynomial rings, matrix rings, and if possible, if I get time, I'll discuss about group rings as well. Now, previously, I've already given a number of examples in rings. For example, I've given some analytical examples and some important algebraic examples like the Hamiltonian quaternion examples. Then the Gaussian integers, quadratic integer rings, examples of such sort. The examples in this lecture to be discussed are of great importance. Specifically, these two abstract structures are very important tools in mathematics. If you take any advanced course on algebra, or rather, if I say, if you take a course on fields, you will be actually dealing solely with polynomials. Okay, we will be dealing solely with polynomials. You'll be what you will be specifically doing is you will be finding the roots of polynomials. You will be finding specific fields such that every root of that polynomial should exist in that field, so on and so forth. Studies of that sort. If I say about matrices, then if you have taken a course on linear algebra, then I guess you should already be acquainted with matrices. Matrices, they occur naturally when one studies linear transformations. They occur naturally when one studies linear transformations, and in fact, if you actually study linear transformations, it's easier to study matrices than solely studying linear transformations, because the properties or the properties of linear transformations that can be actually studied in terms of matrices are quite easily calculated, or the computations become much easier. Okay. For example, there's a concept of eigenvalues and eigenvectors of linear transformations. But calculating that using the linear transformation as a function is quite a very complicated task. But using a matrix actually makes it far easier. Okay, you just need to calculate the determinant of a certain specific form of that matrix and you're good to go. In fact, if you take a higher course on linear algebra, for example, if you take a course on functional analysis or operator theory, operator algebra, the motivation behind such studies are solely finding suitable what should I say suitable conditions for an eigenvalue to exist, and what's the behavior of an operator when it has an eigenvalue or it does not have an eigenvalue, or if you in fact study a bit advanced linear algebra as well. For example, you study orthogonality, you study normal operators, and then self-adjoint operators, unitary operators. In that case, you'll also see that the essence of studying those operators and the essence of studying the matrices associated with those operators are far different from a geometric point of view. If I just say from a geometric point of view, or from a calculative point of view, studying matrices are far more, I would say, relative. I mean, you can relate more to seeing the behavior of a normal operator if I study the matrix associated with that operator. Okay, let's not discuss that anymore. Let's start with these examples. So let us start with the concept of polynomial rings. Okay. Polynomial rings. Okay. So what we do is we start with a commutative ring with unity. So let R be a commutative ring with unity. And what we actually want to do is that we want to give a formal structure of what a polynomial basically is. Now, most of you have already seen what a polynomial is. You have worked with what a polynomial is in your junior classes as well as in your college level math. But this is a sort of uh, a formal introduction to what polynomials actually is on a general note. Okay. So let R be a CRU, a formal expression a formal expression of the form. So the formal expression is given of the form a naught plus a1x and so on till some a n x to the power n, where x is an indeterminate, that is x carries no value. It is an empty box where I can put suitable values to according to suitable conditions. Where x is indeterminate, um, each ai comes from capital R, and this n is a positive integer. Okay, it's called a polynomial. And to be very specific, this is not just a polynomial, but specifically it's a polynomial over R. So it's a polynomial over this given commutative ring with unity. Got it? Okay. And so what I can actually do is that I can just consider this to be some function of x, because after all we are working with a finite case. There are only finite number of components in this expression. So I can assume this to be a finite. Sorry, I can assume this to be a function of x formally. I'm still using the word formally. And using this, I can actually define certain important characteristics or certain important properties of this polynomial. For example, I always restrict the leading coefficient to be non-zero. So this an is called the leading coefficient. This an is called the leading coefficient, and this term an x to the power n, this we will call the leading term. And whenever we will be studying a polynomial, it's always an assumption that the leading coefficient is always non-zero. And the reason is that we have a well-defined object related to a polynomial, which is meant by its degree, and it's the highest power of x possible in that given polynomial. So if I don't assume that the leading coefficient is non-zero, then I cannot say that what's the highest power of x possibly is, because otherwise it will become a zero polynomial, and a zero polynomial is a very trivial case. There's nothing too important to study about that on a general note. So we will always assume that the leading coefficient is non-zero even if not mentioned, and degree of fx is, so in this case we can define degree of fx to be n. Okay, yeah. And specifically, we can also talk about what is the root of a polynomial, but I guess you people should know what a root of a polynomial is. So alpha is said to be, one second, yeah. So alpha is said to be a root of fx, and we know that if f of alpha is 0, right? That is the basic definition of what a root of a polynomial is. And typically studying the roots is some sort of, it's a topic in when we study field theory, and it's quite a bit complicated to talk about roots, not just as simple as it seems when you do your school level math and finding roots. It's quite a complicated task to talk about roots specifically and algebraically and analytically talking about roots, I'm saying. Okay, whatever. And we also know that if I talk about any polynomial over any ring, then it can have only finite number of roots. I'm not talking about it having exactly n number of roots where degree of f is n. Those sort of discussions are solely confined to when the ring we are talking about is a field, and specifically is a complex field, right? So in this case, I'll just say that it has a finite number of roots. Every polynomial can have only a finite number of roots, and that this can just be brought down from the conclusion we have in case of complexes. Whatever. You can also think of it being actually concerned with the divisibility criteria, which you guys already should have known, because I already have a lecture on unique factorization domains and Euclidean domains and principal ideal domains. Then I've discussed what the division criteria or divisibility of polynomials specifically is. And I guess you guys also know what division looks like. So specifically, if I talk about if alpha is a root of f, and let me be specific that alpha is an element from R only, then I can write fx as x minus alpha times gx. And the reason for me to be able to write this is that the division is always confined to the ring we started with, right? So you can easily observe that fx is a polynomial we started with in Rx. Now since alpha is in R, this polynomial is also there in Rx, and gx is also by division in Rx. So this gives you a factorization over Rx. And if all the roots of fx are in R, then I can actually factorize it n times because the degree of fx is n. That is quite visible from here. The problem arises if alpha is not in R. If alpha is not in R, then this factorization is not possible, because in that case, this polynomial you cannot write it as a factor because it is not, it won't be in Rx at that time. So these sort of discussions will be confined to some other lecture on fields. We won't involve in that here. Let's specifically go to a general discussion polynomials. So suppose I start with two polynomials. So I start with Rx, and I have arbitrary two polynomials. Suppose I start with polynomials Px and Qx coming from Rx, and let us give a formal expression to this at that point. Suppose this is a naught plus a1x, and say I have here anx to the power n, and I choose a polynomial Qx, so is equals to b naught plus b1x and so on till b bn x to the power n. Let's say we are saying that both the degrees are same, and the reason is that the addition we will define is actually component wise. That is, see, whenever we talk about polynomials, this actually can be thought of as a collection of n tuples of the coefficients, right? This can be easily observed. So it's b2 and bn, right? And so now it is quite valid that what I mean by component wise addition. So we will be actually adding the coefficients using the addition defined on R, keeping the powers of x as the point, I mean as the components. Okay, so this will eventually give me a0 plus b0 plus a1 plus b1x, and you will get a2 plus b2 times x square, and this will continue till an plus bn x to the power n. Now it's clear enough, if you have more number of terms in either of the polynomials, those terms will just be as it is because it has no component related to it, right? That's why I kept both of them to be of the same degree. Now how to multiply them? The multiplication solely arises by simple multiplication using distribution, and we deal we just kind of consider all of them to be just numbers. So if I multiply say px times qx, so we will just get a multiplication in case of distribution. But to keep in mind that we still need to form a polynomial, that I need to have a coefficient plus a coefficient times x plus a coefficient times x square and so on. And the degree, see, the maximum degree I can actually reach px times qx is x to the power 2n, right? Because that x to the power n times x to the power n, these two terms will give you the maximum possible degree. But the problem will arise if an times bn will multiply to become 0. And that is only possible if we have 0 divisors in the underlying ring R. Because by assumption an and bn are not 0. But if their product gives you 0, then we will have a degree less than equals to 2 to the power n. So I can in fact say this on a general note, that degree of px times degree of qx is less than equals to degree of p plus degree of x. I guess you people already have understood this. Moreover, the equality arises if R is an integral domain. That is, it has no zero divisors. Therefore, there is no possibility for two non-zero elements to get multiplied to become zero. Right? Now, what should be the coefficients if I say? So, if you can just relate to this fact that a naught times b naught will be the constant term. Constant term is the term with no x. then what should be the element which will give you x, or which will act as the coefficient of x? Then you can observe that if you just multiply a1x with b0 and a0 with b1x, you will get the coefficient which will have x. So this is just a0 b1 plus a1 b0. And you can see that this pattern actually follows. If you want to justify what the coefficient of x square should be, you can easily observe that, this should be a0 b2 plus a1 b1 plus a2 b0. And this pattern follows that the coefficient of x to the power n follows as that the indices will eventually add up to n in each term of the coefficient. Got it? Clear? Okay. So you can also write this these coefficients as, so summation ai b to the power n minus I, or let me use the term k minus I, where this should be the coefficient of, so I running from 0 to k, where this is the coefficient of x to the power k. Clear? Got it? This product is also called Cauchy product, and these coefficients are also called Cauchy coefficients. So if in some case you hear the term a Cauchy product or a Cauchy coefficients, they are actually referring to a product of this form. Clear? Okay. Now the question arises that we have defined two operations. So I started with a commutative ring with unity R. Then what can I say about Rx? Now you can easily observe that if R is commutative, then Rx will also be commutative. It will be a commutative ring. Will it have the identity element? Now R has 1, and by the way we have defined multiplication, you can easily observe that the multiplicative identity of R just acts as the multiplicative identity of Rx as the constant polynomial one. So it's in fact a commutative ring with identity as well, or the commutative ring with unity as well. I can say something more. In fact, if I choose any element out from R, suppose I choose a small r and an element from capital R, then I can consider this to be a constant polynomial fx to be equal to R, and then it will also be an element of Rx. So R is actually contained in Rx, and you can also see that R is in fact a subring of Rx, because the operations defined on Rx are typically induced by the operations defined on capital R. Clear? Clear? Okay. Now, what can I say about the additive identity? So the additive identity will also come out to be just fx equals to 0. Fx equals to 0, where 0 is the additive identity of R. So what are the conclusions which we actually get? These are very easy justifications. You can just follow up them from how we define the addition and multiplication over the polynomials. So what I actually conclude is that, number one, R is a subring of Rx in terms of constant polynomials. So let me just specify that. In terms of constant polynomials. Number two, that the additive and multiplicative identities of Rx are simply that of R. As constant polynomials. As constant polynomials. Now we can say something more. Like the statement we gave about degree, let me just verify that once. Suppose I choose out a polynomial, say I choose out a polynomial px to be is equals to 2x square plus 1 and qx to be equals to say 3x square plus 1, and I choose it out from zx. Z66, let's say Z66. Okay. So the operations will be just addition and multiplication modulo 6. That's quite evident. So the operation here will be addition and multiplication modulo 6. One thing I have not discussed here, I should have mentioned that these additions of the coefficients and this product of the coefficients are actually the operations which we have defined on R. Okay. That's not just arbitrary addition and multiplication. So here we know that in Z6 the addition and multiplication are defined modulo 6. So that will be the same definition if when we do it on polynomials. And you can easily observe that if I multiply this out, I'll get 6x to the power 4 plus 2x square plus 3x square, and you'll get then 1. But this will be actually 0 because 6 is 0 modulo 6. So you're just left with 5x square plus 1, right? Therefore, the degree is degree should have been 4, but it's not exactly 4 because 2 and 3 are 0 divisors in Z6, right? But clearly enough, if we had chosen R to be an integral domain, so we have already two conclusion. Number 3, this is quite obvious from here that if R is an integral domain, then so is Rx, because then any non-zero coefficient cannot get multiplied to become 0, and since we consider the leading coefficients to be always non-zero, therefore and so therefore whenever we consider the degree of any product of polynomials, it will be just equal to the degree of p plus the degree of q. Yeah, okay. And obviously we are dealing with non-zero polynomials. I'm not talking about zero polynomials at any cost. Those are not not that important to be studied at this point. So I guess that's an assumption which you can already justify yourself. Okay, right. What more can we say? Yeah, so this part is good. Okay. The another important thing to notice is that number 4. Let me add it separately. Suppose now see. Suppose R is a field. Suppose R is a field. Then the question is, can I say Rx is a field? Rx is a field. Now, see, this actually is not possible, and the reason is very simple. Suppose I choose the polynomial fx to be is equals to x from Rx. Now, this is clearly a non-zero polynomial, and if Rx would have been a field, then this would have a multiplicative inverse, right? And clearly enough, the multiplicative identity is fx equals to 1. So the multiplicative inverse should have been, therefore, fx inverse should have been 1 over x. But you can easily observe that this is no more a polynomial over R. In fact, this is no more a polynomial, right? This is no more a polynomial, and therefore non-zero polynomials, or I'll get something more rather, polynomials with indeterminates typically cannot have a multiplicative inverse. The polynomials which have a well-defined x term, that is well-defined indeterminate term, cannot be having a multiplicative inverse, and the reason is simple. But what can I say about polynomials which only have a constant term, that is constant polynomials? Okay. So let me do it in this way, that let fx gx, or let me use conventionally the things we use for determining polynomials. So let px qx be in Rx, be in b units. Okay, that is they are invertible. So what conclusion can I draw out from here? We have already seen that px and qx, if have a indeterminate term, then they cannot be units. And let me just follow up that mathematically, but that's quite easy to follow. Then px times qx must be equals to 1. So I wrote this in this way. So I should have assumed actually like this. So let px be unit. Then for some qx in Rx. Now this qx is positively non-zero, or obviously non-zero, because in any non-trivial ring we always assume 1 is not equal to 0. That is, the multiplicative identity is never equal to the additive identity. Whatever. But since we are starting with a field, so R is a field, or let me just start with R be an integral domain. This question is already answered, right? That Rx cannot be a field. The most it can be is an integral domain. So we start with R being an integral domain. We start with R being an integral domain. So let px be rx be an unit. So since we are in an integral domain, so we can actually talk about the degree of px times qx to be degree of px plus qx. But the degree on the right hand side is 0. It has no indeterminate term. But degree is always a non-negative quantity, right? And for two non-negative quantities to add up to 0, the only possibility is that both of them are 0. They are in fact non-negative integers. That quite precise to observe is degree of qx. But that essentially means that px and qx are just identically constants. Say we refer to them as p and q. And when they are constant, they are just elements of R. And this simply implies that units of Rx are units of R. In fact, we can also say conversely, but that's an obvious statement, because that is if you start with units of R, if you start with units of R, suppose A is a unit in R, then you can just consider A to be the constant polynomial Px equal to A. And when A is a unit in R, then there exists some element B such that AB is equals to 1. Consider B to be another constant polynomial, say Qx, and then in Rx as well, Px times Qx will give you 1. So units of R and units of Rx are in 1 1 correspondence. Clear? So what we essentially get is that number 4, that units of Rx and units of R are equivalent. And Rx is not a field, even if R is 1. Clear? Got it. And specifically, we are talking about non-trivial rings in thoroughly in any discussion. Clear? Okay. This is a very fine thing to observe. Now, suppose this you should justify on your own. So, do this on your own. That what can I say? What can we say? What can we say about zero divisors? About zero divisors of R, X, and R. Okay, or let me do it. Let me just give a hint. See, talking about zero divisors of Rx and R makes no sense if R is an integral domain. Because we have already seen that if R is an integral domain, Rx is also an integral domain, so it will obviously have no zero divisors. So there's no point of talking about that. So assume R to be simply a CRU. So let R be simply a CRU. And let me take suppose Px times Qx is 0. But this would give that degree of P plus degree of Q is 0 again, and this will imply that P and Q are in R, and PQ is 0 in R. Therefore, the zero divisors of Rx and R are also equivalent to talk about. Justify that, and that will also eventually talk about the fact that if R is an integral domain, so is Rx. Right? Clear? Okay. One more thing to observe is that when we are talking about a polynomial, it's quite important to observe that with reference to which ring we are talking about that polynomial. Okay, so polynomials depend heavily uh, on the ring we are talking about. Okay, we are talking about. What I actually mean is that suppose I choose this polynomial x square plus 1 and I consider to be a polynomial over z, which I can surely do. In fact, I can also consider to be a polynomial over z2x, which surely I can also do. Right? Right. But the important thing to observe here is that, see, x square plus 1 over zx has no roots over z. right? But when I talk about z2x, you can easily observe that x square plus 1, you can write it as x square plus 2x plus 1, but that's exactly x plus 1 whole square, right? If I equate this to 0, I should get the element x is equals to 1 as a root. And you can also verify this by just putting 1 out here, right? Because in this case, the operation is modulo 2. So it is extremely important to check which ring, with respect to which ring we are talking about a polynomial. Whatever, let's not discuss any more about polynomials, but I just giving a few things to observe. That is, if I start with a subring of R, then Sx will eventually be a subring of Rx. That's quite an easy verification. In fact, if I talk about the ring generated by only the square determinants, for example, this will collect the polynomials of the form, say a naught plus a1 x square plus a2 x to the power 4, which are having only even powers of x. This will eventually be a subring of Rx at all costs. Let me just give a question. Justify that the collection of polynomials fx over Rx such that f of 0 is 0, that is it is having no constant term, is a subring of Rx. Okay, try to do this on your own. Okay, okay. Let's now get into the concept of matrix rings. Matrix rings. Let me go to a new page. Matrix rings. Now discussing about matrix rings is quite complicated to the fact that it often does not carry the important properties of the ring we will be eventually starting with. What is the plain and simple definition? Let R be a ring. Let R be a ring. Define M and R to be the collection of all n cross n matrices with elements from R, with each element from R. Clear? Collection of all n cross n matrices with each element from R. So, for example, if I talk about this matrix, say 1, 2, 3, 4, then I can consider this to be a matrix over Z. So this is a 2 cross 2 matrix over Z. In fact, I can also consider this to be a matrix over R, over Q, in fact over C as well, right? Now this is quite important to observe that I can actually talk about a subring of this sort, which you can actually see out from here. But before that, I need to give a ring structure to MNR, and that's also quite obvious. See, we already know that MNR is a additive additive abelian group. It's an additive abelian group with the additive identity being the zero matrix. That is, every entry is zero, being the zero matrix. And this is an obvious observation. Moreover, moreover, considering the matrix multiplication, usual matrix multiplication, I can give a ring structure to multiplications to matrices as well. I can give a ring structure to matrices, to collection of matrices as well, or to MNR, let's say to MNR as well, right? Because if you recall, how are matrices multiplied? So if I talk about two matrices, say A and B, coming from MNR, then AB is defined as the ijth coordinate of AB is simply defined as summation over AIK BKJ K running from 1 to N, where the entries of A are of the form Aij and the entries are of B are of the form Pij. So this is the simple definition, and then this multiplication is defined using the multiplication R. The additions are defined using the additions on R, and therefore this is a well-defined quantity to be contained in M and R itself, right? Hence, we can talk about M and R being a ring. Moreover, if R has identity, if if R has identity 1, then if I choose the matrix say A to be equals to Aij such that this Aij is having the value 1 whenever I is equals to 0 and 0 otherwise. I is equals to j and 0 otherwise. So this is just the identity matrix. This is just the identity matrix, and you can easily observe that this identity matrix actually works as the multiplicative identity of this matrix M and R, right? You can easily follow it up. Okay. Now the things which we should observe is that matrix multiplication is in general not commutative, even if R is so. So matrix multiplication, there are numerous examples you can construct yourself, or you can get on internet. There are numerous examples to check that matrix multiplication is never commutative on its own. So matrix multiplication in general is not commutative. Is not commutative. Okay. Therefore, even if R is a commutative ring with identity, I cannot say that M and R is a commutative ring with identity. Moreover, if R is an integral domain, M and R is still not an integral domain. Suppose R is an integral domain. So this should be an obvious question to ask whether M and R is an integral domain as well. And that's exactly not the case. Because if I choose, suppose say I choose R is equals to Z. Z is an integral domain, and we all know about it. And I choose the ring M2Z. The matrices I choose out from M2Z are suppose 1 0 0 0 and say 0 1 0 0. If I multiply these two out, so these are non-zero matrices on their own. So I'll get 1 times 0 plus 0 times 1. So 0 here, 1 times 0 plus 0 times 0. 0 here, 0 times 0 plus 0 times 1. 0 here, and 0 times 0 plus 0 times 0. So 0 here, right? Therefore, these two are zero divisors in M2Z. In fact, Z was not an integral domain, but still we have zero divisors in M2Z. So therefore, M and R is not an integral domain in general, even if R is so. Clear? Clear. And therefore it's quite obvious that working on general with a matrix ring is quite complicated, because see, in case of polynomial rings, if I know certain properties of the underlying ring R, then I can say a lot about the polynomial ring Rx. But in this case, even if I know some important properties of the ring R, I cannot say things about M and R. So it's actually easy to talk, or to bring down this ring to some easier structure and talk about that. Okay. Now, if you have seen what diagonal matrices are, you should be concerned about the fact that adding and multiplying diagonal matrices are extremely easy. Because suppose you have two diagonal matrices, say 1 2 0 0 and 3 4 0 0, we'll eventually see that the matrix multiplication is just having multiplication of elements along the diagonal component wise. So you will have 1 multiplied to 3, you will get 3 here, you will get 2 multiplied with 4, you will get 8 here, and you have 0 and 0 here, right? In fact, adding is in fact for every matrix it's quite easy, but in this case it's also easy. Thing to remember is that this multiplication is quite easy, and in this case actually, if you collect all diagonal matrix for examples, then you can in fact say that if R is an integral domain, the collection of all diagonal matrices will be an integral domain, provided that diagonal matrices form a ring. So justify collection of all diagonal matrices, over a ring R is an is a ring. Uh, Show that this will suffice actually. Show that it is a subring of M and R because the operations are same, and this is just a sub collection of the all possible matrices. Justify the same. Justify the same for the collection of all upper triangular matrices over R. Clear? Okay. So yeah, these things are very easy to calculate. In fact, upper triangular matrices are also quite less complicated than arbitrary matrices, but in fact, it's quite easy to talk about. And there also comes an important class of examples called the scalar matrices. Now, this can also be easily worked out with. Scalar matrices are thus matrices where suppose I have a matrix A is equals to Aij, where these Aij's are defined to be the same element A for all I is equals to J while it's 0 otherwise. That is, these are just diagonal matrices with every element being identical. Okay, and in fact, you can see that these are just a special type of diagonal matrices and are easier to work with. Moreover, I can actually give a correspondence between this collection of scalar matrices. Suppose I consider the collection of scalar matrices to be S and R. Collection of all n cross n scalar matrices over R. I can have a function from say S and R to R such that I map each matrix A to the element small a in capital R, where this A is the collection of all entries Aij, where the diagonal entries are this element A. Okay, for all I equal to J and 0 other ones. Okay, you can actually see that this gives you a isomorphism. This easily gives you an isomorphism. Is it clear? Moreover, matrices are in fact not invertible in general as well. If you talk about any arbitrary matrix over any arbitrary ring, I cannot say that it's invertible. And this easily follows from the concepts of determinants of matrices, which you should have already known. That if the determinant of a matrix is 0, so I can say that it's if and only if A is not invertible. This is a easy calculation. You can easily check. You can easily go by the formula of the inverse of matrices as well, which follows from the concepts of determinants. So therefore, I can actually talk about a collection of units of M and R, and we know that collection of units of any arbitrary ring actually forms a multiplicative group. So collection of units of M and R is denoted as GLNR. And if you have studied groups, I guess you already know that GLNR is an important class of examples of groups which gives a multiplicative matrix group, right? I guess this part is pretty obvious. You should have read groups, then you will be eventually cleared about what this collection eventually is. So this is the collection of all n cross n invertible matrices over any arbitrary ring R. Clear? Okay. Now, and this is the last observation I would like to talk about. That if S is a subring of R, then M and S is eventually a subring of M and R, and this actually gives you the inequality which we started with an example that I can talk about this matrix being in M2Z, but M2Z will be eventually contained in M2Q, M2Q will be eventually contained in M2R, and M2R will be eventually contained in M2C. Clear? Okay, so that's all for this lecture. In the next lecture, I will be talking about group rings, and then we will be coming up with some important topics as well. Okay, so meet you guys in the next lecture.